welcome you all in the 10th lecture of electronics measurement and instrumentation. In this lecture I will discuss the standard AC bridges. So, this is the outline of my lecture. First of all, I will discuss the inductance bridge, that is the bridges that is used for the measurement of the inductance, that is the Maxwell bridge, Hayes bridge, Owen's bridge. And then I will discuss the capacitance bridge, the bridge that is used for the measurement of capacitance, that is Schering bridge. And then I will discuss the bridge, Wien bridge, that is used for the measurement of frequency. So, first this is the classification of AC bridges as I have discussed already. So, first is Maxwell bridge. So, Maxwell bridge is used for the measurement of inductance, the inductance which can be represented by the series combination of L2 and the resistance R2, that is the leakage resistance. So, here the unknown resistance, unknown inductance, that is L1, and its internal resistance, inherent resistance R1 is shown. Here we have to use in this bridge we are using L2 and R2, and both inductance and resistances are variable in nature. So, to balance the bridge we have to vary L2 and R2 by keeping R3 and R4 is in same condition. We are not varying R3 and R4, but only we are varying R2 and L2 to get the bridge in the balance condition. Balance condition means there is no current through this detector circuit, then the bridge is in the balance condition. So, we know that when the bridge is in the balance condition, it means the voltage at point B and the voltage at point D is same. So, it means ki there is no current through it, no current through it. So, when there is no current through it, it means ki the whole current that will flow through this So, it means ki when there is no current through bridge, means ki a whole current, that is I1, will flow through this. So, I1 is equal to I3, and here I2 is equal to this, I2 is equal to I4. So, same current is flowing. Now, so here in this bridge, Maxwell's inductance bridge, L1 is the inductance to be measured with the resistance, inherent resistance of R1, L2 is the variable inductance, and R2 is the variable resistance. R3, R4 are the pure resistances. So, as we know, the under balance condition, the product of the opposite arms of impedances are equivalent. So, here the Z1, Z4 is equivalent to Z2, Z3. So, by placing the value of Z1, so Z1 is the combination of inductance and resistance, series combination. So, it is R1 plus j omega L1, and R4 is the pure resistance. Similarly, L2 is the inductance, and so in series with a resistance R2. So, it is R2 plus j omega L2 into R3. So, now by solving this equation, we will get R1 R4 is equal to R2 R3, and j omega L1 R4 is equal to j omega L2 R2. So, it means L1 R4 is equivalent to L2 R3. So, by comparing the real and imaginary terms, we will get R1 is equal to R2 R3 by R4, and L1 is equal to L2 by R3 by R1. So, again this is independence of frequency, there is no change in the value of inductance when the frequency of the source is changed, and then there is whenever this bridge is basically used to measure the iron loss of the transformer. So, the Maxwell has proposed one more bridge, that is the Maxwell inductance capacitance bridge. Here the unknown value of the inductance is measured, is compared with the known capacitance and resistance. So, the unknown inductance is shown here as a Lx, and the inherent resistance is shown by the Rx. So, this bridge is compared with the standard capacitance that is C1 in parallel with the R1. So, here we can vary the R3 and R1, and by this variation we can make the bridge in balance condition. So, again here the Z2 is equal to R2, okay, Z2 is equal to R2, Z3 is equal to R3, and this capacitance combination, capacitance and resistance combination means 1 by R, we can say 1 by Zp is equal to 1 by R1 plus 1 by x1. So, the value of x1 is j omega c1, 1 by j omega c1. So, here y1 is equal to 1 by R1, y1 is basically admittance of the capacitance. So, y1 is equal to 1 by R1 plus j omega c1. So, under balance condition we know that Z1 Z4 is equal to Z2 Z3. So, here Z4 is equal to Zx. So, Zx is equal to Zx into Z1 is equal to Z2 Z3. So, we can simplify it that Z1 is equal to Z2 Z3 by Z1, and so Z1 is equal to 1 by Z1 can be represented at Y1. So, we can use this, either we can use it as an impedance or we can use it as an admittance, that depends upon how we can solve the equation easily. So, here we have taken the admittance in place of impedance. So, by substituting all the values, Zx is equal to Rx plus j omega Lx is equal to R2 R3 1 by R1 plus j omega C1. So, again by solving this equation and then comparing the real and imaginary terms, we will get that Rx is equal to R2 R3 by R1 and Lx is equal to R2 R3 by into C1. So, here we can measure directly the value of Rx and R1. Here we can measure directly if we will calibrate the bridge, the detector circuit in such a way. So, we can find out the value of Rx by varying the R3 and R2. So, why we have used this standard known capacitance for the measurement? We can use in previous circuit we have used the inductors, but here we are using capacitance. So, why we are using capacitance here? Because the capacitance are less expensive than the inductors, and capacitors are generally loss free, and then capacitance the in inductor we are using inductors, then there is an electromagnetic field variation is there, and then that will affect the function of the inductor, but external field loss in terms of capacitor is very low, and standard inductors require well shielding to eliminate the effect of stray magnetic fields. So, standard inductors will not present its rated value unless current flow through it is precisely adjusted. Then in comparison to inductance, the size of capacitance is also very small. And one more thing, that capacitance can be fabricated on a chip also, that is not possible for the inductor case. So, advantage of Maxwell bridge. So, Maxwell's bridge, basically the balance equation is independent on losses associated with the inductance, and it is also independent of the frequency of the measurement. Then scale of resistance can be calibrated to read inductance directly, and scale of R1 can be calibrated to read the value of Q directly. So, this Maxwell bridge, both the bridge are suitable for the medium Q coil, Q of the coil. Suppose it can the coils can be measured whose the Q value is between 1 to 10, and R1 is very high in this case. So, commercial Maxwell's bridge that is available in the market is basically measure the inductance from 1 to 1000 Henry with plus minus 2% of error. Then next is Hayes. This bridge is proposed by the Hayes, and this is basically the modification of the Maxwell's bridge. Here the in the series the inductance which is represented by L4 and in series with the R4, in series with the inherent resistance R4, that can be compared with the standard C1 and R1. So, here the balance condition is achieved by varying C1 and R1. So, here we can see that this C1 and R1 is series combination. So, we can write Z1 is equal to R1 plus 1 by j omega C1. So, that is Z1 is equal to 1 plus j omega R1 C1 by j omega C1. Similarly, Z4 is the series combination. So, it is R4 plus X4, and X4 in place of X4 we can write j omega L4. R2, Z2 and Z3 are pure resistances. So, it is R2 and R3. R4, now in the balance condition, what will Z1, Z4 is equivalent to Z2, Z3. So, we can find out Z4, Z4 is equivalent to Z2, Z3 by Z1. So, by substituting these values, Z4 R4 plus j omega L4 is equivalent to R2 R3 by 1 plus j omega R1 C1 by j omega C1. So, now solving this equation, we have to solve this equation. So, for solving this, we have to multiply the numerator and denominator by 1 minus j omega R1 C1, because we have to segregate the real and imaginary terms. So, by multiplying this, the denominator term will not have a j term. So, this is the equation. Now, we can segregate the real and imaginary terms. So, by segregating this in real terms, we will get R4 is equal to omega square C1 square R1 R2 R3 by 1 plus omega square R1 square C1 square. And by comparing the imaginary terms, we will get omega L4 is equal to omega R2 R3 C1 by 1 plus omega square R1 square C1 square. So, this is the equation. Now, this this equation has a frequency term. So, how we can avoid this frequency term, that we will see. So, here we can see that in case of inductor, the inductive component is leading with the resistive component, and in case of capacitor, the capacitive component is lagging with the resistive component. And since both the angles in balance condition, since these are in the opposite arms, so the both the tens of both the angles should be same. So, here we can find out that the tan theta L is equal to XL by R, that is equal to omega Lx by Rx, and for the capacitance theta C is equal to tan theta C is equal to Xc by R, that is equivalent to 1 by omega C1 R1. Now, in both cases the tan theta L is equivalent to tan theta C. So, by solving this equation, we will get omega Lc by Rx is equivalent to 1 by omega C1 R1. So, the Q is equal to, this is equivalent to Q. So, Q is equal to 1 by omega C1 R1. Okay. So, now if we substitute this Q, the value of Q is equal to 1 by omega C1 R1 in this equation. So, in place of omega square R1 square C1 square, we can write 1 by Q square. Similarly, here we can write 1 by Q square. So, when we place this Lx value is R2 R3 C1 by 1 plus 1 by Q square. So, if the value of Q is more than 10, then this term will be 1 by 100, that is 0.01. So, this when this term is 0.01, so it means this term will not affect the value of Rx Lx very much. So, we can ignore this term, and then Lx is equal to R2 R3 C1. So, this bridge is Hayes bridge is basically used for the high value of Q. If Q is more than 10, then only this component which we are measuring is free from the frequency component. So, Hayes bridge is used for the measurement of the inductance whose Q is very high, that is at least higher than the 10, and if it is less than 10, then this term has a significant and we can't neglect the frequency term. So, commercial Hayes bridge measure the inductance between 1 microhenry to 100 microhenry with the error of plus minus 2%. Next is the Owen's bridge. So, Owen's bridge is also used for the measurement of unknown inductance. Here it is compared with a capacitance. So, in this bridge two capacitances are used, one is in the circuit, that is single C1, and second is the C4 in combination with R4. and this is the unknown inductance. So, this unknown inductance is used is measured in comparison with the known standard two capacitors, that is C4 and C1. So, again we can write that Z1 is equal to minus j by omega C1 because it is a capacitance, Z2 is equal to R2, Z3 is equal to R3 plus j omega L3, and Z4 is equal to Z4, this is that is R4 plus X4. It is basically we can write R4 plus X4. So, X4 is X4. So, that X4 is equal to 1 by j omega C4, and then multiplying j by in denominator and numerator we will get this value. So, when under the balance condition we know that the product of opposite arms are equivalent, means the product of this XC1 into this XC3 is equivalent to R2 into this, we can see XC4. So, that Z1 Z3 is equivalent to Z2 Z4. So, it is not always true that Z1 Z4 is equivalent to Z2 Z3, but it depends upon the what we have nominated the different components. So, in this base it is Z1 Z3 is equivalent to Z2 Z4. So, by substituting the values of Z1 Z3 Z2 Z4 we will get this equation, and again here we can compare the real and imaginary terms. So, in real terms, imaginary terms we will get R2 R3 is equal to R2 C1 by C4, and by comparing in real terms we will get L3 is equal to C1 R2 R4. Again this bridge has a advantage that there is no frequency component in the balance equation. Next is the Schering bridge. Schering bridge is basically used for the measurement of capacitance. So, here as we can see that the AB arm consists of R2 and this consists of C1 in parallel to R1, and this consists of C4, R4 and C3. So, here Z1 is equal to basically parallel combination of R1 and C1. So, Z1 is equal to R1 parallel X1, Z4 is equal to Z4 in series with this. So, it is R4 plus X4. So, now by substituting this value Z1 is equal to, Z1 is the parallel combination of R1 C1. So, as we have seen in the previous sections that the Z1 will be R1 into 1 by j omega C1 divided by R1 plus j omega 1 by j omega C1. So, Z1 we can write in this way. By solving this equation we will get Z1 is equal to R1 by 1 plus j omega R1 C1, and Z2 is the pure resistance. So, Z2 is equal to R2 and Z3 is a pure capacitance. So, it is equivalent to 1 by j omega C3, and Z4 is the series combination of a resistance and capacitance. So, it is equivalent to R4 plus 1 by j omega C4. So, by solving Z4 is equal to 1 plus j omega R1 C1 by j omega C. Now, again we have to substitute these values in the balance condition equation. So, under balance condition as we know that Z1 Z4 is equal to Z2 Z3. So, here Z4 is equal to Z2 Z3 by Z1. So, by substituting all values, this is the value of Z4, then this is the value of Z2 Z3 divided by Z1. So, we will solve it like this stepwise, and then after solving this equation appears, and here we can see we can again compare real terms and imaginary terms, and we can find out the value of the unknown resistance and unknown capacitance, that is the C4 and R4. So, unknown capacitance is C4 is equivalent to R1 C3 by R2, and the unknown the inherent resistance of the capacitance, that is shown by the R4. R4 is not a separate resistance value, it is the resistance which a capacitor offers because of the dielectric. So, R4 is C1 R2 by C3. So, again the advantage of Schering bridge is that the value of resistance R4 and capacitance C4 are independent of the frequency. So, we can measure the dissipation factor also by using this Schering bridge. So, we know that the dissipation factor in the series circuit, series RC circuit is D is equal to resistance by the capacitive inductance. So, R4 by X4. So, X4 is equal to 1 by omega C4. So, it is omega R4 C4. So, that is the dissipation factor, and that is equivalent to omega R1 C1. So, dissipation factor tells us about the quality of capacitor, how close the phase angle of the capacitor is ideal to 90 degree. So, dissipation factor we can find out by calibrating the scale in terms of C1 at one particular frequency. So, in Schering bridge we can find out the dissipation factor of any capacitor at a particular frequency. It means if we change the frequency, the value the dissipation factor will change. So, similarly, if the resistance ratio is maintained at fixed value, then the dial of C3 can be graduated in terms of direct reading of the C4. So, similarly, we can directly compare the C4 in terms of C3. So, commercial Schering bridges are used to measure the capacitance from 1 picofarad to 1000 microfarad with the accuracy of plus minus 2 degree of. Similarly, there is a question to design a Schering bridge if having capacitance of 0.8 millifarad in parallel with 1 kilo ohm resistance, and second arm consists of 3 kilo ohm resistance, the third arm consists of an unknown resistance whose value we have to find out. Then there is a fourth arm consists of a capacitance of 0.4 millifarad. So, we have to find out the unknown capacitance value when the we have applied a source that is having 1 kilohertz of frequency. So, again hence R3 this is ohm, not in watt, it is ohm. So, again this is also a kilo ohm. So, omega is given. So, we know that Rx is equal to C4 R3 by C2 and Cx is equal to R4 C2 by R3. So, by substituting the value we can find out the value of Rx and Cx. We can also find out the value of this dissipation factor, that is D is equal to omega Cx Rx. So, we can substitute the value of omega by using this frequency, omega is equal to 2 pi f, and by substituting the frequency value we have to find out the dissipation factor. So, the dissipation of this capacitor is 5.011. Then Schering bridge, for the measurement of small capacitance we are using a Schering bridge which has a very high voltage. So, in this we are using a transformer with high secondary winding, so that it can increase the voltage at the input of this Schering bridge, and we are using a line frequency, power line signal in the transformer. So, a small capacitance with dissipation factor is usually supplied from the high voltage and high frequency source. So, this is the circuit arrangement. Here we can see that we have used transformer and we have shielded all the components, so that the stray capacitive field will not affect this measurement, and generally we can use the transformer with the power supply. And for the detector circuit we know that since it is an AC bridge, so we have to use a vibrational galvanometer, we can't use the normal galvanometer in this. So, next is Wien bridge. Wien bridge is generally used for the measurement of frequency, and if we can replace this detector by an amplifier, and when the bridge is in imbalance condition, not in balance condition, then we can also use this bridge to produce a frequency. That means we can use it as an oscillator also. So, and if the bridge is in the balance condition, we can use it for the measurement of the frequency of any oscillator or the any circuit which is producing AC signal, repetitive AC signal, periodic AC signal. So, measurement of frequency of voltage source, here the voltage source Vs is applied whose frequency is not known. So, this is the Wien's bridge. Here we are using one series combination of capacitance and resistance and one parallel combination of capacitance and resistances. So, again we know that under balance condition we know that Z1 is series combination. So, Z1 is equal to R1 plus 1 by j omega C1, Z2 is equal to R2, and here we have written parallel combination. So, we have written is at admittance. So, admittance is equal to 1 by R3 plus j omega C3 and Z4 is equal to R4. So, under balance condition we have to vary R3 to balance the bridge, and under balance condition means when there is no current through the detector circuit, then Z1 Z4 is equal to Z2 Z3, and by substituting the values R2 is equal to R values of Z1 Z4 Z2 Z3, we will find out this equation, and by solving this we will find out these terms, and then by separating real and imaginary term we will get R2 by R4 is equal to R1 by R3 plus C3 by C2, and in second term we are getting omega C3 R1 is equal to 1 by omega C1 R3. So, here we can find out omega square is equal to 1 by C1 R1 C3 R3. Okay. So, omega is 1 by omega is equal to we know 2 pi FC f. Okay. So, by substituting this omega is equal to 2 pi f, we get f is equal to 1 by 2 pi root C1 C3 R1 R3. Now, generally R1 is equal to R3 and C1 is equal to C3. If we put R1 is equal to R3 and C1 is equal to C3, then we will get here C1 is equal to C3 and R1 is equal to R3, we will get the frequency f is equal to 1 by 2 pi r. So, this is in this method we can find out the frequency of the unknown curves. So, in this lecture I have discussed the different type of AC bridges that are used for the measurement of inductance, capacitance and the frequency of any unknown component. So, sometimes we have a problem with this capacitance and other things, that there is stray capacitance produces. So, to avoid this stray capacitances there are a Wagner ground connections. So, what we will do, we are using one more resistance and capacitance combination, and these C1 C2 are showing the stray capacitances. So, here what we will do, first we will put the switch at one position and then we will balance this bridge by seeing that there is no current through the tree. Then second time we will put this switch at this position, and then by varying our W we will see the bridge is in balance condition. Then by just varying from 1 to 2, switch from 1 to 2, and then regularly we check whether the bridge is in balance condition or not. So, when the bridge is in balance condition at both the positions, then that means that there is no effect of the stray capacitance. So, okay, that is from my side. Thank you all.